Hey guys, so we're going to look at a few examples here that deal with Newton's second law, which says that the acceleration of an object is directly proportional to the magnitude of the unbalanced force that's causing the acceleration and inversely proportional to the mass of the object. And we see this through the equation A equals F net divided by M, or the net force divided by the mass of the object. This can be reorganized where F net equals acceleration times mass, and mass equals net force divided by the object's acceleration. Now the first one we'll look at here is pretty straightforward. An unbalanced force of 14 newtons acts on a 58 kilogram mass for 12 seconds. Determine the acceleration on the mass. So a couple things that we know here. We have an unbalanced force of 14 newtons. We have a mass of an object that is 58 kilograms. And we know that the time that this happens, fix my T there, is 12 seconds. We want to know what the acceleration of this mass is. We currently don't know that. Now to give you an idea what's happening here, and again, you should always be drawing a sketch. This is a 58 kilogram mass that is being, or has a force applied to it of 14 newtons in some direction. Now Newton's second law will tell us that this object will accelerate in the direction of the unbalanced force. So we see from the question that an unbalanced force of 14 newtons is being applied to the right. So our object should accelerate in the direction of that force or to the right. So using A equals F net divided by M, we know the net force to be 14.0 newtons divided by the mass of the object, 58.0 kilograms. This will give us an acceleration of 0.241 meters per second squared. So it's 0.241 meters per second squared. That's being applied in the same direction as our net force of 14 newtons. Now the second one here, a 6 Newton force gives a mass M1. So the 6 Newton force gives a mass M1, an acceleration of 7 meters per second squared. A different 24 Newton force gives another mass, we'll call that M2, the same acceleration, 7 meters per second squared. What is the ratio of M1 to M2? So a couple things that we know here. We know that the force 1 on the first object is 6 newtons. And the force on the second object is 24 newtons. We know that the acceleration on the first object is 7 meters per second squared, and that is the same for the second object as well. What we don't know is the ratio of M1 over M2. That is our unknown. That's what we're going to try and look for here. Now we know that our equation can be reorganized to solve for mass, where the mass is equal to the net force divided by the acceleration. That's just rearranging our original equation. So if we use this and apply this to both forces, so for example mass 1, F1 was 6 newtons, and the acceleration is 7 meters per second squared. For M2, we know that the force is 24.0 newtons divided by the same acceleration of 7.0 meters per second squared. Now, if we look at the ratio of M1 to M2, well, we have both of those pieces listed here. Here's M1, and here's M2. So if we plug that in, we end up with 6.0 newtons over 7.0 meters per second squared. We'll put all that over the 24 Newton force of the second mass over the same acceleration. Our accelerations being the same will cancel from each other. And our ratio becomes the first force, the ratio of the first force to the second force, which is 6 over 24. Same units, so the ratio comes out to 1/4. The ratio of M1 to M2 is 1/4. Seems kind of like a long roundabout way of getting there, but nevertheless. Last example here, we have two forces being applied to a 5.6 kilogram box that's originally at rest on a horizontal frictionless surface. Love that. Determine the magnitude and direction of the acceleration of the box. Okay, so the first thing I want to do here is kind of get an idea. So this is our free body diagram. We have our box there. We are showing the forces acting on the box. Some of the things that we don't see on here would be our weight or force due to gravity, which we'll get into shortly here, well, in our next unit. But we're just really need to pay attention to the F1 and F2 that are going to cause this box to move left or right on this plane. And I'm going to start by saying the negative direction is going to be to the left, and the positive direction is going to be to the right. Now we have this F2 acting at an angle here of 38 degrees. And we know from what we've previously learned that all of that 9 newtons is not being pulled along the same axes that the 3 Newton force is being pulled, along that horizontal x-axis. So what we first have to figure out is, well, of this 9 Newton force, how much of this is acting along the x-axis in the same or opposite direction of our 3 Newton force? So to figure that out, we're going to resolve that 9 Newton force into the x component, which we have 9.0 newtons times the cosine of 38 degrees. This gives us an A of x equal to 7.1 newtons. So this force right here this A of x is equal to 7.1 newtons. That's the value that we want to use in order to find our net force. Now this becomes a simple problem of vector addition of two vectors acting in opposite directions. So if we add these head to tail, we get our resultant. And I'll do this algebraically in a second. Our resultant looks something just like that. Now algebraically, if we add these together, again the negative direction meaning to the left, so this force becomes minus 3.0 newtons. We'll add that using vector addition to the x component of our 9 Newton vector, which was 7.1 newtons, positive because it's moving to the right. This gives us a net force of 4.1 newtons. So this other piece here would also be 4.1 newtons. Now that's given us the net force. That is not what we're looking for. We're looking for the magnitude and direction of the acceleration of the box. Now we know that to find acceleration, we take the net force and divide it by the mass. In this case, our net force is 4.19 newtons acting to the right in the positive direction. We'll divide that by the mass of the box, 5.6 kilograms, which gives us an acceleration on the box of 0.73 meters per second squared. And since this is positive, our acceleration is going to be to the right, 0.73 meters per second squared, in the same direction as our net force of 4.1 newtons. Make sure you bring your questions to class. Good luck.